puede ocultar. Pero las cosas que no salen bien no se dicen.
Welcome to the next lecture in the Physical Verification series for VSD. In this lecture, I'll take a deep dive into design rule checking, otherwise known as DRC. It's hard to understand design rules if you don't know how chips are manufactured. And while this is probably well known to most, if not all of you, it's worth making a really quick recap of what a silicon manufacturing process does. Most common silicon manufacturing processes are planar, meaning that materials are deposited on top of or implanted into a substrate, which is most often a silicon wafer. Then more materials are deposited on top in layers or planes, thus the name planar. Transistors, resistors, capacitors, diodes, wires, and so forth are all defined by geometry drawn in these layers, mostly done in lots and lots of rectangles. The way materials get turned into geometry on the chip is to use a combination of light, photoresistive material, and masks. Masks are basically extremely high-resolution stencils made with an opaque printed surface on glass. The way almost every process layer is made is to grow a layer of material over the entire wafer, such as silicon dioxide or polysilicon or metal. Then a thin layer of photoresistant material is put over the whole wafer. After the photoresist dries, a mask is put on top and the wafer is put under a high-intensity light. Where the mask is opaque, the light is blocked, and where the mask is clear, the light shines through to the photoresistant material and breaks it down. Once broken down, the photoresist can be washed off, leaving behind a pattern in the photoresistive material. These patterns are used in several different methods. One is ion implantation to dope the material in places not protected by the photoresist. Another is an acid etch to remove material from places not protected by the photoresist. Making wires and metal layers is an example of something done with an acid etch. Adjusting transistor thresholds is an example of something done with ion implantation. Now, you've probably have heard the phrase Moore's Law used many, many times, although it's often quoted without regard to the underlying reason that it exists. The reason that, over time, you can fit more transistors into the same amount of space is that the machines used to make the masks and the machines used to shine light through the masks get better in every generation. Regardless of how you make a chip, it will be done using various pieces of machinery, and those machines will have limits on what they can do. Those limits translate into limits on how small you can make the geometry on the mask before you start running into yield losses. There are additional constraints caused by various parameters of the process that the manufacturer chooses to use, such as the amount of time spent etching the layer, the angle of the etch, the materials used, and so forth. The manufacturer will make lots of test wafers where they make lines at different widths, spacings, angle, and such, and then probe these lines after manufactured to determine where lines got shorted together or broken. Shorts and opens are generally caused by spot defects in the deposited materials subject to the rating of the cleanroom environment, and those defects will have some distribution, which is going to be a normal distribution. So there will always be something that will kill a chip. But all the different bits and pieces, including the cleanliness of the manufacturing space, the tolerances of the machines, and the DRC rules, combine to give a mean expected rate of failure in parts per million. That determines, for a production run, approximately how many dead chips you will end up per batch. The portion of working chips that you get from the total number of chips manufactured is called the process yield. The goal of the design rules is to make sure that every part of the chip has about the same rate of failure. You don't want one metal layer having more failures and creating more dead chips than another metal layer or a transistor gate or any other part of the design. So as I work through an explanation of each design rule, bear in mind that there is a reason for every rule having the dimension that it has. And every rule is not some magic number where if your spacing or width is below that number, your chip will fail. It's all about probability of failure and yield of parts. Rules can always be made more conservative than the minimum. Finding the absolute minimum distance rules for every layer will produce reliable chips with the maximum density of circuitry. It also means sometimes that the rules themselves are complicated. There is some trade-off between having a rule that allows the absolute densest to design versus having a rule that the tools, namely the design rule checker, can compute in a reasonable amount of time. For the designer, though, the bottom line is that a certain number of rules are considered non-waivable, and the manufacturer will not accept a design if any non-waivable rule is violated. If you're violating even one of those rules, even by just a little bit, your design will be rejected until you fix it. That's why it's important to have software to do the design rule checking, so that you can know that your design is good before you submit it to the manufacturer. As I did for the first lectures, I'll use the open source PDK from SkyWater Foundry. In the first lecture, I showed where to find the online design rule documentation for the SkyWater process, which I'll repeat here. It's https://136.org.read-the-docs.build/en/136/rules.html. As I work through various rule types, I'll point out where in these web pages you can go to find out more information on the specific rule I'm explaining. I'm going to illustrate each rule both from the SkyWater documentation and with the layout editor Magic, which many of you may already know I'm the developer of.
Y entonces cuando yo voy a cogerlo, porque lo iba a mover, porque estaba apoyado en la mesa de papi, el cuadro estaba suelto. No estaba cogido con...
Sí, no. No, nunca estaba cogido.
Siempre estaba cogido, ¿no?
Nunca estaba
Bueno,
cogido.
estaba cogido, pero...
The most basic and simplest rule is width. If any material is too thin, then a large enough spot defect can create a break in the material and result in an open circuit. Most routing is done at the material minimum width. The rule presumably had this in mind, so there's no harm in keeping all wires at minimum width. Just be aware of how much resistance you accumulate over a long distance run. Minimum width for implants is a different problem, though. Since implants are diffusing into the material underneath, they often have a somewhat fuzzy boundary. Below a certain width, it will start acting like there isn't any implant there at all. There are additional complications having to do with the angle of implant and crystalline structure of the silicon and such that are too arcane to discuss here, but they all factor into why the width rule is what it is. The width rule is fundamental to the process because every process is named after the feature size. That is, the SkyWater 130 nanometer process is so named because it has a feature size of 130 nanometers, or 0.13 microns, which is the minimum length of a transistor. And that means, more generally, the minimum width of the polysilicon layer, which forms the transistor gates and therefore defines the transistor length. That value is something of a misnomer in the SkyWater process because if you work with the various design tools, you'll find that the minimum width of polysilicon is actually 0.15 microns, as is the minimum length of most low-voltage transistor gates. Why this is so has a fairly complicated history, but it comes down mostly to the fact that the process was originally designed for memory chips. And memory chips are made of the same circuits put down in large arrays, and so the core circuit can be heavily optimized for the regularity of the geometry. So the bottom line is that they can get the transistor length down to 130 nanometers in these heavily hand-optimized core memory cells. But to the average circuit designer, the process looks more like a 150 nanometer process. Spacing is the next simplest design rule. For the opposite reason as the width rule, if two wires are too close together, then a mask or material defect can cause them to short together. There are several complications to the spacing rule that have to do with optical effects of the mask. One is the run length rule, which states that if two wires run in parallel for some minimum distance, then they require greater spacing between them. There are no run length rule requirements in the SkyWater 130 nanometer process. The other complication is the wide spacing rule, which states that if a wire or some piece of layout is wider than a given distance, then other wires of any width must keep away from it by an additional amount of space. For processes with very small feature sizes, like 65 nanometers and down, there are multiple grades of rules for wires of different width. This relates to what I said earlier about rules being too complicated for the design rule checker. The wide spacing rule really represents a continuum of minimum spacing versus wire width, and from that continuum, the rule deck can specify one conservative distance for everything, or two distances, or three, or four, or whatever. The more gradations of the wide spacing rule that the rule deck has, the denser the layout can be made. And the more gradations there are, the longer it takes for the rule checker to check everything. The SkyWater 130 nanometer process has only one set of wide spacing rules for metal width of greater than 3 microns. This is called huge metal in the rule documentation. Although 3 microns doesn't seem particularly huge, but it's the width of metal that triggers the wider spacing requirement. This value of 3 microns is common to all of the metal layers. Notch rules are basically spacing rules. A notch is technically a different geometry than what invokes the spacing rule, but I have not seen a rule deck that specified a different distance for a notch than for any other spacing type, and so notch and spacing rules are generally bundled together under the same rule. Minimum area rules and maximum area rules are both designed to avoid delamination issues, at least for metal layers. Tiny pieces of metal can become detached. However, the same thing can happen with very large metal areas as well. Small bits of metal floating around on the chip surface and shorting other things is of course likely fatal to the chip, but a capacitor surface delaminating will be pretty fatal to the capacitor too. There are no specific maximum area rules in the SkyWater technology for other than vias, which are usually defined with a fixed width and length, implying both a minimum and maximum area. These rules are made to control the via resistance and provide the best contact between layers. Minimum area for implants and diffusion is just like the minimum width rule for implants and diffusion. There must be a sufficient amount of stuff being diffused. Because diffusion and implants aren't things that can delaminate, there are no maximum area rules for these layers. For metal layers, though, there is a complementary rule to the minimum area, which is the minimum hole area. Small holes in a metal layer will make it more likely that the oxide grown over the layer won't completely fill the hole. Vias are the connections between different metal layers, made with a contact cut, which is a hole made in the oxide down to the metal layer below, and filled with another metal layer, often aluminum or tungsten. Because it connects the layers above and below, the positioning of a hole relative to the layers is critical. The holes are made with a separate mask, and so the design rules are all related to the ability to keep the masks in alignment so that the cuts in the oxide remain firmly over top the metal underneath. In many modern back-end processes, the contact cut is the exact same area as where the two minimum width metal routes cross each other. The SkyWater 130 nanometer process is a bit more conservative than that, specifying an amount of material surrounding the contact cuts on all of the metal layers except for the lowest ones. Vias have several kinds of rules, and they differ a lot depending on what the metal layers the contact cut connects. The simplest one is a simple surround rule, meaning that the contact cut must be surrounded by a minimum amount of material on all sides of the contact. But there are also extension rules, which are often presented as a directional surround and often with rather confusing language for the rule. The rule for via 3 in the SkyWater process, for example, says via 3 must be enclosed by metal 3 on one of two adjacent sides by at least 0.09 microns. What this means is better described by an illustration. Due to another via 3 rule, there's a basic surround requirement of 0.06 microns. Combined with the extension rule, or directional surround rule, whatever you want to call it, it means that the metal covering the via must be longer in one direction than the other. In one direction, the width of metal under the via can be as short as the via width, which is 0.2 microns, plus the minimum surround of 0.06 microns on either side, for a total of 0.2 plus 0.06 plus 0.06 is 0.32 microns. But then in the other direction, the minimum width of metal must be at least 0.2 plus 0.09 plus 0.09, or 0.38 microns. So every via 3 must have a plate of metal underneath that is at least 0.32 microns by 0.38 microns. It's worth taking a moment here to point out some of the quirks of the way that the layout tool Magic presents layers to the user. Magic was written as a designer's tool for doing layout, so it tends to present a view of the layout to the user that is supposed to let the user more easily grasp what is going on in the layout and to keep things relatively simple to make it easier to create designs quickly and efficiently. There are two main ways it does this, which differ from the way layers end up in the masks, and because of that, the layers that are shown in Magic don't quite match up with the rules as they appear in the Foundry documentation, which is based on masks. The first of these has to do with vias, which is why I'm talking about it now. The masks for a via can be considered to consist of one or more contact cuts in an array, plus the surrounding metal layers on top and on bottom. In other words, Magic distinguishes between the idea of a cut, which is a single contact cut, and a via, which is a single area that connects two metal layers together with one or many contact cuts. To simplify the layout view and also to simplify the processing, Magic draws the whole via as a single layer. This layer, in effect, contains top and bottom layer metals plus any number of contact cuts, depending on how large the layer is drawn. This makes it easy to create and manipulate large contact array areas without worrying about where the cuts are. In fact, Magic has a fairly complex cut generating algorithm, which means that you can draw a ring of contacts, such as what you would use for a guard ring connecting well or substrate around a device, as a single ring-shaped via. Magic will automatically figure out how to put the maximum number of cuts into the area that follows all the design rules and also places them symmetrically along the sides and also with cuts in each of the corners. The user doesn't have to worry about any of these details. However, it is important to understand that particular definition of a via implies that the via layer that is drawn in Magic must include the minimum amount of surrounding material on both sides. This has an unfortunate side effect, which is that the width and spacing of the via as drawn in Magic doesn't seem to match up with the documented design rules. In the design rule violation explanation that I put in the Magic technology file, I try to be helpful by explaining that the rule in Magic is equal to the sum of several of the SkyWater rules. In general, you don't need to care what the dimensions are, only that they are all internally self-consistent within the Magic tech file, so that if Magic's DRC engine says that you aren't violating any of Magic's rules, then you aren't violating any of SkyWater's rules. The automatic generation of contact cuts means that most of the VIA rules are correct by design and you don't need to worry about them. Magic will flag an error if the area is too small for a contact cut. Local interconnect is an interesting property of the SkyWater process that isn't found in many Foundry processes. Most processes go straight from polysilicon on one layer to an aluminum metal layer directly above it, which is metal 1. Polysilicon is a very high resistive material. It's the perfect material for transistor gates, but a lousy material for drawing wires. It is usually silicided, which means that it's metallized on top with a thin coating to lower the resistance, but it still doesn't meet the definition of a routing layer. But polysilicon is used mostly for transistor gates, which means it isn't current carrying. If it isn't carrying current, then there's no IR drop along the length of it. Then there will be some delay in charging the gate due to the RC time constant formed by the resistance of the poly and the capacitance to ground, but that's a minimal concern for small amounts of poly forming transistor gates in a circuit. Local interconnect is another problem. Because it is presented as a routing layer, it should be thought of as a current carrying layer. But it is formed from titanium nitride, which for resistance is somewhere about halfway between polysilicon and aluminum. Here are the resistances per square in the SkyWater process. Polysilicon is about 50 ohms per square, which is quite high and suggests that it isn't silicided. Local interconnect is 12 ohms per square, while metal 1, which is the routing layer above local interconnect, is 100 times less. So the resistance of local interconnect is significant. This leads to some rules for local interconnect that are awkwardly stated and difficult to implement, such as a requirement that the aspect ratio of any uncontacted wire of local interconnect cannot be more than 10:1. This is, largely speaking, an uncheckable and unchecked rule, And in fact, it is more of a design guideline than a specific rule. The important thing for local interconnect is to treat it more like polysilicon than like metal. Don't route with it like you would route with metal layers. That's why it's called local interconnect. It should be kept to a minimum and used only to connect neighboring circuits together, not as a long-haul signal routing. Any use in a current-carrying wire should be checked by the designer for IR drop. Generally, when making devices in the SkyWater process, the device terminals like transistor gate, source, and drain should be contacted up to metal 1 directly above the device. The PDK device generator for the SkyWater process in Magic has a checkbox option for contacting device terminals up to metal 1 inside the automatically generated cell. This checkbox is marked by default and should be only unchecked if the designer knows what they're doing. Front-end rules affect all process devices like transistors, resistors, and such. They tend to be a lot more complicated than back-end metal rules. There are usually a handful of rules that are specific to each device in the process. Fortunately, the designer usually doesn't need to worry too much about the device-specific rules. The PDK includes an automatic parameterized device generator, and the purpose of the device generator is to draw a complete device that satisfies all of the design rules automatically. In most layout tools, the designer is presented with mask layers, and creating a device that satisfies all of the associated design rules is both difficult and painful. Magic's way of hiding most layers associated with the devices means that it is relatively easy in Magic to just draw devices by hand. A transistor is just a rectangle of polysilicon crossing a rectangle of diffusion. Magic treats poly and diffusion like they belong to the same mask, not like one layer over top another layer. It's an unusual way to think about poly and diffusion, but works well in practice, since in a CMOS process, poly never overlaps diffusion without forming a device. So when poly is drawn over diffusion in Magic, both are replaced in the area of intersection by a different layer type, which is the device. The device can then be replaced by any of several different varieties to get similar devices, like a low voltage threshold or a high voltage threshold device. In the process, those devices differ by the presence or absence of implant masks. In Magic, they differ only by the device type. The associated implant masks are taken care of automatically by Magic when it writes GDS, along with satisfying the DRC rules, which for implants are mostly limited to minimum width, spacing, and area. So generally, the front-end DRC rules are of concern to a designer only in limited circumstances. The average digital designer will use standard cells, which are guaranteed to be able to be placed by abutment in rows without violating any DRC rules. The average analog designer will use large arrays of fingered devices generated from the PDK parameterized device generator. People who are designing standard cells or creating special device layouts because the PDK device generator doesn't provide what they want are the ones who will need to pay the most attention to the front-end device DRC rules. MOSFET transistor rules are pretty basic, which is why it is feasible, especially in Magic, to draw them by hand. Each device type will have a minimum gate length and minimum gate width. Like contacts must account for any misalignment of masks, a transistor gate must account for the alignment between the diffusion masks and the polysilicon mask. That means that the polysilicon must extend beyond the diffusion by a certain minimum distance to account for the vagueness of the diffusion boundary and the alignment of the masks. This is the basic extension rule for transistors. Since poly over diffusion always forms a transistor, it is important to make sure that poly that is not supposed to be part of a transistor stays away from diffusion so as not to overlap and form an accidental transistor. That determines the poly to diffusion spacing rule, which is usually very small. The poly to diffusion spacing in the SkyWater process is only 0.075 microns, and the distance to tap is only 0.055 microns. There is also a rule specifying how close a source or drain region can come to the gate. The source or drain region contact can come to the gate. As I've already mentioned, different devices are defined by implant layers. Sometimes, for the aid of the circuit extraction, the device may be marked by an ID layer. ID layers have no DRC rules associated with them, except usually they are required to completely cover the device. To Magic, the ID layers and the implant layers are very similar. Since they're used to define a specific type of device or a specific set of DRC rules for a device, Magic just defines a new device type. So in Magic, a standard threshold P-type MOSFET has a device type PFET. A low threshold, low voltage P-type MOSFET has a device type called PFET LVT. A low voltage P-type MOSFET inside a standard cell has a device type SC PFET. This is exactly the same as a regular PFET device, except that SkyWater has relaxed the contact distance rule inside standard cells. So the different device type tells Magic's DRC engine to use the different distance rule. This leads to a bit of a conundrum for a person who wants to design a standard cell. The relaxed rule in SkyWater is actually cell name specific. In other words, the relaxed rule has been thoroughly checked by measurement for the standard cell sets that the Foundry provides. So if the user uses the relaxed rule outside of an area marked with the standard cell ID layer, then it will be a primary rule violation and cause the design to be rejected by the Foundry. But if the device is used with the ID layer, then the design will be flagged as having a standard cell ID layer on a cell that is not approved by the Foundry. These layers are dealt with in Magic by specifying them as locked layers, which by default are not editable by the designer. But a designer who is making a standard cell that follows the design patterns of an existing standard cell layout should be free to use the special device types with the standard cell ID layer. The error kicked back by the Foundry about unauthorized cell names is not a fatal error and won't cause a design to be rejected. After all, Google encourages experimental design, and the designer accepts the risk of violating DRC errors in a way that can be considered to be relatively low risk. But if you're concerned about risk-free design, then don't use the locked layers. The greatest complexity to the designer is the placement of wells and taps. The digital standard cell libraries in the SkyWater process are, with the exception of the high voltage library, designed with taps in a separate cell. A tap is a region of diffusion that is doped with the opposite implant type from a transistor source or drain. So, for example, a P-type MOSFET sits in an N-well. The diffusion for the P-type transistor is, as the name implies, doped with a P-type implant, which then forms a PN diode barrier between the transistor diffusion and the surrounding N-well. The tap, then, is a region of diffusion that is also inside the N-well and is doped with an N-type implant. Since the diffusion and the well are of the same type, there is no p-n junction and they are electrically connected together. The tap forms the connection to the well to set the bias voltage, specifically so that the p-n junction formed between the transistor and its surrounding is firmly reverse biased, keeping the transistor from leaking more than a tiny amount of current. The standard cell taps follow one set of rules, which keeps p and n-type diffusion separated by a minimum distance, which is another DRC spacing rule. However, there is an alternative method called a butted tap, which has the transistor source and the tap sharing the same diffusion region. The difference between the transistor source and the tap is defined by an implant mask. There are extra rules associated with how close a tap region can get to a transistor gate and the minimum length for such a butted tap. Most Foundry processes have same net spacing rules pertaining to wells. These are difficult rules to check, since understanding whether the rule is violated or not depends on understanding the electrical connectivity throughout the whole circuit, which is a computationally expensive task. The rule most often applies to N-well regions and states that if two N-wells are on different nets, or more specifically at different voltages, then the spacing between them has to be larger than the otherwise stated minimum distance between two N-wells. SkyWater doesn't have a same net spacing rule on N-wells generally, although there is a rule for the distance between low voltage and high voltage wells. I'll cover high voltage rules momentarily. Another somewhat complicated design technique is to isolate an entire circuit area using a deep N-well. This is a technique required by standard CMOS technologies where the underlying wafer, called the substrate, is doped to be electrically conductive, usually with a p-type dopant, And then N-type regions are formed by implanting N-type dopant into areas of the substrate to form N-wells. What that means is that the substrate is tied to ground, the N-wells are tied to a power rail, and P-type transistors in their N-wells are all nicely isolated and pretty well noise isolated from ground. The N-wells are all isolated from one another too, and so they can be biased to different voltages. The N transistors, however, are all tied to the P substrate, so the voltage under the gate of all these devices is by definition zero or ground, and all the devices are directly exposed to the substrate noise, which is the noise being generated by every other device connected to the substrate. To get around the problem, the foundry defines a deep N-type layer called the deep N-well. It is buried far down into the substrate, far enough that P-type dopant can be diffused into the region above it so that it becomes an N-type layer sandwiched between the P substrate below it and the P-well above it. To keep that P-well region above it isolated, the deep N-well layer is fenced in on all sides by a regular N-well. The result is that you can have alternating N-well and P-well regions, both of which are isolated from the substrate. The P-well can be biased to other than ground, and noise generated by the transistors is mostly limited to the P-well region. There are a host of DRC rules associated with the deep N-well. First, it has a large minimum width requirement. The fence of N-well around it is also a requirement, and that fence has to overlap the deep N-well layer by a minimum amount on both the inside and the outside. Deep N-well layers have a huge minimum spacing, which is 6.3 microns in the SkyWater process. Deep N-wells work best when they are either covering entire circuits for noise isolation, allowing the backgate connection of an N-type transistor to be above ground in an analog circuit, or allowing the creation of a vertical NPN-type bipolar transistor. I mentioned high voltage rules earlier. The high voltage implant serves two purposes. First, the implant makes the N-well under a P-type transistor, as well as the source and drain regions of both N and P transistors, tolerant of higher voltages. In the SkyWater process, the implant allows for voltages up to about 5 to 5.5 volts, which is considerably higher than the standard voltage of about 2 volts for transistors that don't have the implant. The second purpose is to define a thicker gate oxide underneath the transistor gate so that the gate-to-source voltage can be higher without triggering gate punch-through. The high voltage implant layer is defined by a mass called HVI. The higher voltage affects the DRC rules for everything inside the high voltage region. So the diffusion layers have greater width and spacing requirements. The N-wells have a larger spacing requirement both to themselves and to low voltage wells. Transistor gates must be both wider and longer. Pretty much every rule pertaining to diffusion in poly has a different value when inside a high voltage layer. In the SkyWater documentation, these rules are in separate sections that extend the rule sets for diffusion, tap, and poly. In Magic, the best way to represent high voltage regions is, again, to use different types. For various obscure reasons, the one thing that Magic doesn't do is to define a separate high voltage N-well type or for poly, but it does define different layers for high voltage diffusion and high voltage tap layers. These are marked as MV-diff, or medium voltage, to distinguish them from the really high voltage devices formed with another implant layer called UHVI that allows voltages up to 20 volts. Unless designing 3.3 to 5 volt standard cells, say, most designers will just want to create high voltage devices using the PDK device generator. Resistors can be very complicated in the SkyWater process and so have lots of associated design rules. Resistors can be made from polysilicon, diffusion, or a P-well region inside a deep N-well. The diffusion and well resistors are somewhat less useful because they have a p-n junction connection to the surrounding area and so will leak slightly and must be kept at a firm reverse bias. The poly resistors are most useful and come in multiple varieties, with standard poly having a resistance of 50 ohms per square, as I mentioned earlier, and with specially doped poly having resistances of 320 ohms per square called XHR for extra high resistance, and 2000 ohms per square called UHR for ultra high resistance. The XHR and UHR polyresistors have very specific requirements for the contacts, with rectangular instead of square contact cuts and tightly restricted values for contact cut placement and spacing. Magic works well with these because it can generate those cuts exactly as specified automatically, and the designer only sees a contact region at the end of every resistor with simple DRC rules for width, spacing, and distance to the resistor device. Again, though, most designers will want to use the PDK device generator to create resistor devices, and being an analog component, there are a few cases in which it would make sense to draw a resistor by hand. Capacitors can be a complicated subject. There are 4 distinct types of capacitors in the SkyWater project. Varactors, MOSCAPs, vertical parallel plate capacitors, otherwise known as MOM capacitors, and MIM or MIM capacitors. Varactors are formed like MOSFET transistors, except using a tap layer for drain and source instead of regular diffusion. The tap layer, of course, connects directly to the surrounding well, so this is not a transistor in the usual sense because you can't put current through it. But it does have a capacitance between the gate and the channel under the gate, which is all connected together with the source and the drain, and that capacitance varies a lot with the voltage differential across the gate. Varactor DRC rules are like MOSFET transistor rules, but with some different requirements for width, length, gate extension, and contact distance from the gate. MOSCAP capacitors just use a standard MOSFET transistor gate-to-channel junction as a capacitor. This forms a sort of weak varactor. Its best use is for decoupling caps between power and ground, where the capacitance per unit area is high and the voltage across the capacitor doesn't change. Since MOSCAPs are just transistors, there are no special DRC rules pertaining just to MOSCAPs. Vertical parallel plate capacitors are also called MOM capacitors for metal oxide metal. These include purely plate capacitors formed by stacking a plate of one metal over another. However, to maximize the amount of surface area of the capacitor, they're usually made of interleaved fingers of metal, making use of the sidewall capacitance, or capacitance between the vertical sides of facing metal fingers. They can combine both types with interleaved fingers and multiple stacked metal layers. The DRC rules for these just follow the DRC rules for metal layers. There are no special rules for plate capacitors. However, to ensure that the value of capacitance is known, it is recommended to use only the pre-drawn layouts provided by the foundry, as these have been characterized and have known values. Determining the capacitance of an MOM capacitor by extraction is tricky and usually comes up with a poor approximation of the actual value. There's almost no reason to use vertical parallel plate capacitors in a process that offers MIM caps. MIM stands for metal insulator metal. While technically that's the same thing as metal oxide metal, the name MIM refers to a device made with some extra processing steps between standard metal routing layers to create an extra plane of metal between routing layers with a very thin layer of insulation between the additional plane and the route layer underneath it. So these devices can have a much, much larger capacitance per unit area than a fingered metal capacitor. The SkyWater process sets that capacitance at 1 femtofarad per square micron. That's smaller than what you'd get from a MOSCAP, but the resulting capacitance is perfectly linear. Naturally, there are a host of DRC rules associated with MIM caps, and pretty ornery ones at that. Most of the rules are not related directly to manufacturing, but rather to ensure that the value comes out to the advertised 1 femtofarad per square micron. That includes both minimum and maximum width rules for the inside capacitor plate. And the metal plate underneath has to have a certain amount of surrounding material. The SkyWater process defines dual layer MIM caps, and the best reason to have dual MIM caps is to stack them on top of each other to get twice the amount of capacitance as you would with just one. There are additional rules for MIM caps, including the spacing between bottom plates, an aspect ratio limit, and a limitation that the capacitor top plate must be rectangular. The MIM caps are usually strictly subject to antenna rules as well, which I'll cover in a bit. Diodes are formed by the p-n junction between diffusion and well. As such, diodes are formed every time you make a transistor or put down an N-well or a deep N-well. These usually unwanted devices are called parasitic devices. So an actual diode device designed into a circuit is really nothing more than a parasitic diode that has been flagged as a circuit device. So diodes are formed more by ID layers than anything else. The ID layers don't have an associated DRC rule, but the diodes just follow all the DRC rules for diffusion, tap, and well. The best way to make diodes, other than parasitics, is from the PDK device generator. There are also standard cell diodes that are used primarily to resolve antenna rule violations, which I will cover shortly. There are a number of devices that the Foundry has created reference layouts for and thoroughly characterized. These are considered to be fixed layout devices. They are guaranteed to be DRC correct by design, and the designer only has to satisfy spacing requirements between the fixed layout device and everything around it. In the technology file for Magic, I make a lot of use of the fixed layout devices to avoid representing a number of design layers at all in Magic. If a layer has design rules, but that layer can only be used in one kind of device, and that device has only one approved layout from the Foundry, then there's not a whole lot of point in representing that layer as a user-editable design layer, because there isn't anything that the user can do with it. For the SkyWater process, that includes the ultra-high voltage implant layer, but also covers a bunch of specialty DRC rules related to high voltage extended drain devices, bipolar transistors, best practice layouts for RF transistors, photodiodes, SRAM core cells, non-volatile memory core cells, and a handful of others. These devices are all found in the SkyWater FDPR library and have associated layouts as GDS. The designer just instantiates the pre-designed cell and doesn't worry about the DRC rules.
No ese sonido, pero una detrás de la otra sin parar.
There are a handful of miscellaneous rules in the SkyWater process that are not particularly layer specific. These are presented in the process documentation under the X category. One of the rules is the off-grid rule. There is a manufacturing grid defined for the process, which is 0.005 microns or 5 nanometers. All geometry in a design layout must have vertex coordinates that fall on a grid point. Magic is especially good at dealing with off-grid errors because it has an internal integer grid that is pegged to the minimum manufacturing grid, and so it is actually impossible to create geometry in Magic that is off-grid. Unlike every other layout tool, Magic has a special way of defining non-Manhattan geometry as all right triangles inside rectangle areas conforming to the internal integer grid, so that the non-Manhattan shapes vertices must fall on grid points. There is only one way to create an off-grid point in Magic, which is to overlap two non-Manhattan shapes on the same layer in two different overlapping cells. Magic will automatically flag such a violation. Another miscellaneous rule is the limitation of angles on layers. Generally, the smaller the feature size of a process, the more limited the geometry. In the SkyWater process, some layers are restricted to Manhattan geometry, meaning everything must be drawn in rectangles. However, all shapes of all layers in the SkyWater process are limited to 45 degrees, and some, like diffusion, poly, local interconnect, and contacts and vias, are limited to 90 degrees. There are a number of these miscellaneous rules that concern the seal ring, which is the area around the outer perimeter of a full chip design, which protects the whole chip when the wafer is scribed and diced. The seal ring layers have all sorts of unique rules, and so in the technology setup provided for Magic, the seal ring is treated like a fixed layout device. The seal ring isn't technically a fixed layout device because it isn't actually fixed. It has to grow or shrink to match the size of the chip design. But it's treated the same way. All the special seal ring layers are part of the GDS for the seal ring and aren't even presented to the user or represented at all in Magic. The whole seal ring is just DRC correct by design. In the technology set up for Magic, it's essentially a handful of fixed layouts that are stretched or tiled together to create the finished seal ring at the correct dimensions for the chip. You might call it a semi-fixed layout. Early Earlier, I described what a tap is, how it is different from regular transistor source and drain type diffusion, and I mentioned that it connects directly to a well or substrate so that the well or substrate can be biased to keep all the parasitic p-n junctions reverse biased. When a parasitic p-n junction becomes forward biased, it creates a condition called latch-up. In essence, there are not just p-n junctions, but PNP and NPN junctions. These form truly lousy bipolar transistors, but they are transistors nonetheless, and they will behave like transistors by shorting the emitter to the collector when the base to emitter junction becomes forward biased. This will effectively short an entire chip, and because it's positive feedback, the chip will be stuck in this state until power supply is removed. That's why it's called latch-up. To get a chip to latch up, one or more of these p-n junctions that are being reverse biased by the tap connections has to become forward biased. The most common way for latch up to happen is that the p-n junction, say under a transistor, is far away from a tap, and so the voltage local to the junction can be very different from what it is at the tap, and the junction can be forward biased. So the latch-up DRC rules declare a minimum distance from a tap connection to any bit of diffusion in a design. The whole perimeter of the diffusion area is a p-n junction, and so any part of the diffusion area could potentially become forward biased and trigger a latch-up condition. SkyWater has a basic tap-to-diffusion distance of 15 microns to prevent latch-up. It also has a very difficult to analyze rule that the tap-to-diffusion distance should be 6 microns for any circuit within 50 microns of the pad frame. Because it's difficult to analyze, it's just enforced by an ID layer. The ID layer is called low tap density and should be dropped into the middle of the chip, 50 microns inside the pad frame border, so that the DRC engine knows to apply the 15 micron rule inside that area and the 6 micron rule outside the area. That's one of those soft rules where in reality there's a gradient of required tap distance, but a gradient rule for tap distance would be virtually impossible either to apply, analyze, or enforce. So instead you get the somewhat odd-seeming rule about tap distance changing at 50 microns inside the pad frame border. Antenna rules are a very different kind of rule because instead of dictating how to avoid a physical manufacturing defect, they dictate how to avoid an electrical manufacturing failure. Antenna rules have the oddball property that they depend on the chip layout at specific points during the manufacture of the metal layers. To put it as succinctly as possible, a long metal line that isn't attached to anything that sinks current can accumulate charge during manufacturing. If that charge has nowhere to go, then it can build up to extremely high voltage. That high voltage will punch through the first thing that exceeds a breakdown voltage, which is usually a transistor gate. So the antenna rules apply to long strips of metal with one end tied to a transistor gate and the other end unterminated. Now usually nobody draws long unterminated strips of metal on a chip, but they do draw lots of metal routes, and often the end of a long metal route connects up to the next metal layer above it. Now during manufacturing, when that metal layer has just been put down on the chip, but the layer above it hasn't, that thing is a wire with one end attached to a gate and the other end unterminated. So before the layer above it has been manufactured, it can build up charge and destroy the transistor that it's connected to. The antenna rules are designed to check when such conditions occur. The rule specifically defines what is the largest ratio of the total amount of metal by area to the total amount of transistor gate by area to which it's attached. This rule has to consider that condition for the state of the design at each step of the metal layer manufacturing. The way that the rule is calculated differs from one manufacturer to another, and that's a lot of detail I'm not going to get into here. One way to avoid antenna violations is to place a diode from anywhere on the route violating the design rule to ground. That can be a parasitic diode. It's really just a piece of end diffusion on the P substrate with the end diffusion connected up to the wire. The hard part about antenna violations is detecting and fixing them inside a big digital standard cell design. It's really up to the placement and routing tools to do that automatically because it's a difficult to impossible job to do that by hand. Typically, if there's a problem, it comes from top-level routing that is done by hand in which the routing tools didn't analyze. Most typically, it comes from some long wire connections between, say, a pad frame cell and a core cell. Ideally, you first minimize such problems by having diodes already built into any input on either the I/O cell or the digital block that is otherwise connected only to transistor gates. If there are any remaining errors, then they can be fixed by connecting down to a diode. If you really understand the nature of the antenna violation, it is also possible to fix the violation just by changing the route layers, by transitioning quickly from the gate input to the highest metal layer used in the route. Stress rules are related to metal delamination, as I discussed earlier in the lecture, and to metal cracking and other damage caused by too much mechanical stress on the chip, especially during sawing and dicing, but also during wire bonding and even basic handling. To mitigate the effect of mechanical stress on metal layers, very wide metal layers often have slotting rules to specify that a wide strip of metal should be perforated with slots to keep any part of the metal from exceeding some maximum width. The slot should be in the direction of current flow. SkyWater doesn't have any specific recommendations for slotting on internal metal areas, although a good rule of thumb would be to stick to the 30 micron by 30 micron limit that is specified for MIM caps. But there is such a rule for a chip's critical sides or critical corners. But in practice, these stress rules are essentially like fixed layout rules. The critical sides and corners are areas close to the edges of the chip where they are subject to sawing and dicing stresses. But that means that they're inside the area of the pad frame, and so if the pad frame cells are designed to meet the stress rules, then the designer doesn't need to worry about them.
Ese es el tercero.
Ah, ¿lo ves en el tercero? ¿En el tercer día?
No, el tercer día ya es el último día.
Metal route layers manufactured on a chip are only as good as they can be kept flat on top. Any deviation from flatness on any metal layer affects all the layers manufactured above it. The manufacturing process of metal layers, perhaps surprisingly, involves physical polishing or actually grinding down the surface to a desired flatness between layers. To achieve that desired flatness, though, the chip has to have a certain amount of flatness before the polishing step. Silicon dioxide and silicon nitride, which are the insulating layers used between metal layers, deposit just like snow falls on the ground. And if you look at the ground after a snowfall, the shape of anything that was on the ground is still seen in the surface of the snow, just smoothed out. Well, metal wires on a chip are bumps on the surface and will make bumps in the insulation grown on top. The best way to minimize the amount of bumpiness is to make sure that the surface is uniformly covered by metal all over. That's what's meant by density in the density rule. Too little metal density and the metal wires are going to show up everywhere as bumps on top of the insulation. Too much metal density causes too much oxide deposition compared to areas of lower density and can result in uneven polishing. The ideal metal density usually falls around 60% coverage or so, and there's a pretty broad range of density that is sufficient to meet the requirements of the polishing process. The good news is that there are automated tools that can generate fill patterns to satisfy the density requirements. The even better news is that it is actually rather difficult to create a layout that can't meet density after applying automatic fill generation. The technology set up in Magic for the SkyWater process has a complicated script that does the automatic fill shape generation, which includes a full set of checks to make sure that the density requirements have been satisfied by the automatic pattern generation. The bad news is that analog designers justifiably hate fill patterns because they are essentially extra capacitance all over the circuits that is difficult to analyze and compute intensive to simulate. There are only two solutions for the analog designer. One is to do the difficult analysis and simulation, which means to go ahead and generate the fill patterns either automatically or by hand, extract the parasitic capacitances from the fill patterns and plug that into the simulations and account for that effect in the analog circuit design. The other is to place fill blockage layers over critical parts of the analog design. The automatic fill pattern generation script must then honor the fill blockage layer and will not generate fill patterns inside that area. Unfortunately, that is the one way that makes it possible for the automatic fill pattern generation tools to fail to meet the fill density requirements. In the very, very worst case, you might end up having to go talk to the foundry about putting your design in a specific spot on the reticle to minimize the effect on manufacturing. It's really best if you don't have to go there. But there are a few things like large spiral inductors that don't give you a whole lot of choice. There are other occasions when automatic fill generation fails to reach the necessary density. This usually happens under fairly rare circumstances, usually because there are stripes of metal placed at just such a distance that the fill generator can't fit fill patterns between them. And if the situation is repeated enough across the chip, then there may be insufficient area where the chip fill can go and density won't be reached. Usually this is just a matter of realizing there's a pathological situation in the layout and to change the metal pitch so that it's no longer a problem. Also, placing metal in extremely high density across the chip can cause failure in the other direction, and since fill pattern generators can only add material, not subtract it, then there's nothing that the automatic tools can do about it, and the designer has to get rid of some of that metal somehow. The good news is that it's really quite difficult to put down that much metal on a chip. We did find one counterexample to that on the first SkyWater MPW run, which is that the digital standard cell decap fill cells had about 90% of the area covered by local interconnect, so that the digital standard cell designs that did placement at low density and filled the rest with decap cells were failing local interconnect density. To fix that, we had to redesign the decap standard cell.
And the first quarter, that is this one, is going to be mandatory. So it's going to be
There are
Fridays
a number of rules that are called recommended rules in most boundary processes, and SkyWater is no exception. The idea of recommended rules is that following these rules will make a design more robust and improve yield. The idea of improving yield makes a lot of sense for a production run when you might be making millions of copies of a chip design. For a shuttle run, the recommended rules are largely meaningless, unless you have a high confidence that you're testing a design that could go straight to a production run, in which case you might want to cover as many recommended rules as you can so that you can be sure that you're testing the design that is as close to the production design as you can get it.
We talk about robotics, we talk about
The recommended rules include such things as having more than one contact cut for every via
but we don't
area.
know exactly what the other things
The recommended rules are denoted by the flag RR in the rule documentation. Violating these rules will not cause a design to be rejected by the foundry, nor will the foundry require a waiver. There are actually only a handful of these rules in the SkyWater process.
We are teaching new
As I just
courses,
mentioned,
and we are
recommended
organizing
rules
those
sort
courses
of define the difference between a test chip and a production chip.
Please,
However, test chips can go a lot further in ignoring design rules. A production chip that has 5% yield loss is a disaster, while a test chip that has a 20% yield loss can be perfectly fine depending on the circumstance. For the test chip designer, the main concern is the set of rules known as manufacturing rules, which are the ones that will cause your design to be immediately rejected by the foundry if you violate even a single one by the tiniest amount. Also, as I mentioned earlier, Google wants designers to do highly experimental things on the SkyWater process, and that often means violating a design rule here and there. For the SkyWater MPW runs, eFabless does a final sign-off using only the manufacturing rule deck. The rules I covered in this lecture, up to and including the miscellaneous rules, are all considered manufacturing rules. The latch-up, antenna, and stress rules are all rules that can be violated with any risk assumed by the designer. Density rules are considered manufacturing rules, although marginally failing designs can sometimes be accepted. Antenna and stress rule violations can lower the yield significantly, but the designer of a test chip doesn't necessarily care that much. Latch-up rule violations may reduce the range of conditions at which the chip operates correctly, but again, depending on the circumstance, the designer may not care.
That's why we are so diverse.
Rule violations that persist in the final design require a waiver from the manufacturer, which is a statement verifying that the customer agrees to accept any risk arising from such rule violations. For the SkyWater shuttle runs through eFabless, all designs have essentially a blanket waiver on all violations that are not manufacturing violations, so the MPW customers don't need to be concerned with the whole waiver process. But in general, for chip submissions for manufacturer, this is something that you'd be required to do. I would be remiss in talking about physical verification without mentioning electrical rule checks. Electrical rule checks, or ERC, are checks for layouts that is DRC correct but would cause circuit failure due to electrical problems. These include electromigration, or the damage to metal wires caused by carrying too much current over a period of time, and overvoltage, especially where high and low voltage circuits are combined. Some overvoltage issues are not obvious, such as the SkyWater rule HVNwell.10, low voltage NWell and high voltage NWell should not be on the same net, and depending on the circumstance, it may not be an issue. Most ERC issues, unless severely in error, are more problems for production runs than for test chips. Apart from a short bit about how Magic describes via layers differently from other layout tools, I haven't said too much about how to run DRC in Magic, or select DRC checking styles, interpret DRC results, or fix DRC errors. The purpose of the following lab exercise is to do all of those things. The purpose of the lecture was to teach you all about the different types of DRC rules and what they mean and why they exist. Now that you understand all of that, I can show you by example how to work with the layout in Magic and how to find, analyze, and fix all sorts of DRC rules. So thank you for listening to this lecture, and on with the lab.
Personal information. I studied their physics degree in the Francisco C. Caldas in Bogotá, Colombia.
Welcome to the lab portion of the third lecture on the SkyWater Open PDK and physical verification. This set of lab exercises is designed to give you hands-on experience with design rule checking using the open source layout design tool Magic. We'll be working partly from a Git repository that I've created and uploaded to GitHub, and partly from the files that come as part of the SkyWater PDK. First, you'll need to clone the repository, so from your virtual desktop, do git clone https github.com r.timothy.edwards vsd_drc_lab.git. This will download all of the exercises we're doing in the lab today. Then cd to vsd_drc lab. Now I've created a simple shell script launcher to run Magic with the preferred graphics, which is OpenGL, and to load the SkyWater PDK so that you're working in that technology as soon as you start up. So you can get started with Magic right away simply by doing run_magic on the command line. Now you've got Magic running. That was the easy part. But let's keep it easy for the first part and just run through a few of the basic DRC errors. Go to the menu item File Open and select exercise1.mag from the list of files in this directory. Here we see 4 basic rules, the ones that I covered first in the lecture. Now, instead of learning about the rule, you'll learn how to fix them. If you aren't familiar with Magic, then I'll tell you the basic things you need to know as we work through the exercises. You can use the Z and Shift-Z keys to zoom in and out. Without the Shift, you zoom in, and with the Shift, you zoom out. If you want to zoom to a particular spot on the layout, you need to use the cursor box, which can be manipulated with the left and right mouse buttons. The left mouse button to move the box by positioning the lower left corner, and the right mouse button to place just the upper right corner of the box. You can zoom to the area of the box with Control Z. So I just zoomed to the area of exercise 1A. Here I have a width error. The pink color is metal 2, and the white dot pattern shows where the error is located. There are commands you can run in the console window, but for now we'll use the menu, so put the cursor box around the area of the error with the left and right mouse buttons, and then select menu item DRC, Report. The report tells you what any errors are that are showing inside the cursor box. In this case, it should be telling you that there is a metal 2 width error. and that the rule is that metal 2 needs to be at least 0.14 microns wide. This is rule MET 2.1, which is a cross-reference to the SkyWater documentation in readthedocs.io. You'll note that there was a key binding listed next to the menu item, which is a question mark. That means that at any time you can type the question mark on the keyboard while your cursor is in the layout window, and it will also give you the DRC result. Try that now. Now to fix the error. In many cases, you'll want to know how much you're violating the error by. So let's select the bit of metal that's in violation. Put the cursor pointer over the metal, zoom in if you need to, and type S, which is another key binding, this one for the select command. Note that I'm also using the mouse scroll wheel to pan up and down. By pressing the shift key while using the scroll wheel, I can pan left and right as well. You can also do that with the keyboard arrow keys. Just a quick note, now that you've selected the metal, type the question mark again. It will say no errors found. That's because it looks for errors only inside that box, and once you've selected something, the box adjusts to what you selected. So now the error is just outside the box, and reporting errors inside the box means that there isn't anything to report. The white dots that show the error extend out to the distance of the violation. So if this rule says that the width has to be 0.14 microns, then you know that the white dots indicate the amount of area that needs to be filled with metal 2 to get to 0.14 microns. First though, let's just measure the width of what we've got. For that, use the B key. This gives you the dimensions of the cursor box. Generally, what you're going to care about is the physical dimensions, so look at the first line, which gives the output in microns. For the record, the lambda value is set to be hundredths of microns, otherwise known as centimicrons, and the internal value, which is always integer, is set to the minimum manufacturing grid, which for the SkyWater process is 5 nanometers. For helping to visualize measurements, you might want to set the grid. Go to the menu window and select, say, grid 0.1 microns. This gives you grid lines of 10 to the micron. If you want to keep geometry snapped to that grid, you can select window snap to grid on, which will force the cursor box to always be aligned to the grid lines. You can stop that behavior with window snap to grid off. Now let me go back to selecting the metal with the S key. The box dimensions I captured earlier say that the piece of metal is 0.06 microns wide, so it definitely does not meet the minimum width requirement. 2 ways to get it to the 0.14 micron width required by the rule. One is to manually set the cursor box around the error area like this. And then, with the mouse pointer hovering over the metal, click the middle mouse button. The middle mouse button is running a command that says, sample what's directly under the pointer and then paint that into the whole area of the cursor box. When you did that, the error paint went away. If you type the B key, it tells you that the metal is 0.14 microns wide, which satisfies the metal width requirement. Now I'm going to undo with the U key once to undo that paint, and once more to put the box back where it was before I adjusted it. I know that the error says that my metal has to be 0.14 microns wide, so I can just set it to exactly 0.14 microns wide without having to worry about manually adjusting the cursor box. I'll use the colon key to redirect keystrokes to the console, and then without moving the pointer out of the layout window, I'll type the command box width 0.14 microns and hit return. Now I'll paint in the same way, just to show you the difference between using the mouse buttons to paint and running the command. So colon key to redirect text, then paint M2. All of these methods have the same effect, which is to make the metal strip wider and solve the error. Going on to exercise 1B. Here we have a spacing rule violation. Now you should know the drill. Cursor box over the area of the error and the question mark key to see the error message. In this case, it's the spacing between metal layers that triggers the error. Since that's an error that works both ways, either left to right or right to left, the white error dots indicate the errors both ways. So if you start at the left bit of metal 1 and draw the box to cover the error area, then type B to get the dimensions, you'll find that the error on that side extends to the width of the spacing error, and the error is symmetrically repeated on the other side.
It's important.
Solving this one requires moving things around, a little different than what we did for 1A.
We are afraid of that.
Select the right side shape with the S key, and then use the right arrow on the keypad, which is keypad key 6, to move the shape away from the other to increase the spacing.
Radicals free is the characteristic of their half energy, maximum energy. Yes, this energy permits that they modify of the membrana of the bacteria, that the break of the
I did this in steps, so if I want to undo that, I'd have to undo several times. Another note to make here. At the top of the window, I get a DRC count, and the goal of this exercise, and most exercises in this lab, is going to be to knock that number down to 0. Since you probably weren't looking at it while moving things around, watch it now while you use the left and right keypad keys to move in and out of an error condition. You'll see that the number changes as the error is made and fixed. You'll also note that the two symmetric sides are counted as two separate errors. Magic doesn't try to figure out what root causes are, it just counts things, and since it is looking for spacing errors in both directions, it will count them twice. When moving things, you're less likely to use the command line, but for the record, here's how you do it. Create a square of metal 1 next to the exercise, like this. First, form the cursor box and then use the middle mouse button sample and paint function. Now adjust the box to cover the right half of that square and type the A key for an area select, which means to select what is inside the cursor box and only inside the cursor box. Now I could use the keypad arrow to move the box to the right like I did before. Since the shapes are attached and I know that they need to be separated by 0.14 microns, I can do move east, type move east 0.14 UM, where E stands for east and move means to move the selection. The commands move, stretch, and box move will be very handy for solving DRC problems.
The hydrogen produced on the process of the hydroxyl of their
Okay, go down to exercise 1C. Here's an example of the wide spacing rule. Type question mark to see the error. This is actually two errors. One is a regular spacing error and one is a wide spacing error triggered by the large metal shape on the left. The size of metal that triggers a wide spacing rule is 3 microns by 3 microns minimum. You can confirm that by selecting the shape with the S key and confirming with the B key that the rectangle is, in fact, larger than 3 by 3. Since this is just another type of spacing error, we solve it in the same way by selecting either shape. So let's say we'll select the small one and use the keypad to move it away. Now, the regular spacing error is 0.3 microns, and once we move that far away, the basic spacing error goes away. This is not a symmetric spacing error, and it makes a difference which edge is being looked at to see if an error occurs or not. Regardless, though, it's still a matter of just keeping on moving the shape until the error is resolved. And so that's what I will do. And now the errors are down to 2. Last error. I mentioned that a notch error is just another way of specifying a spacing error. However, fixing it is slightly different. You want to stretch part of the shape rather than moving something. For example, to solve this, I could try what I did in the example above it and select the top half of the shape, an area select, or the A key, and then move it up, but that just split the shape in half. And underscores the fundamental difference between magic, which has a concept of paint, and other tools which have the concept of objects. Anyway, what I want to do is to stretch the shape up. For that, I'm going to use the same keypad key, but I will use it with the Shift key pressed down, so Shift keypad 8 to stretch the selected shape up. Like any simple spacing rule, it's checked in both directions and so counts for 2 errors, and when that's resolved, the error count goes down to 0. You can use stretching to solve width errors too. To the side of this figure, draw a narrow line in metal 4, narrow enough to fail the width rule. Now this time, to solve the width error, select half of the shape with the A key, and then use Shift keypad 6 to stretch to the right, like this.
For 1 hour, for the organize the atoms in the structure crystalline of the titanium.
For stretching large distances, you probably don't want to do it by keypad and auto-repeating. Say you put down another strip in metal 5, which has a pretty big width requirement. The question mark DRCY command tells me that I have to stretch it out to 1.6 microns.
What is XRD?
With an area select and the keypad, I can stretch it all the way out,
Ask questions.
or I can just redirect to the console again with the colon key
Why is that important?
and type
Yes. What do you
stretch east
What can you learn from the
1.6 microns. Now that's a bit wider than absolutely necessary, and maybe I don't care, or else I can now use the keypad to fine-tune the width back to the minimum, like so, watching for when the DRC error gets triggered.
The way the atoms of the material are arranged.
And there's the error, and I'll move back out, and it's gone. Okay, if you have 0 DRC errors, then you're done with exercise 1. Save it if you want with the menu File Save and click on Write. Now we'll move on to exercise 2.
You can know some of the properties of the material. Yes.
So this would this tell you, in your earlier slide, you said you had a nitrogen in there somewhere that you needed. So would this tell you if you have the nitrogen?
I'll assume that you still have Magic running. You can keep it going for all of the exercises. So just go to the menu item File Open and select exercise 2.mag from the list of files in this directory, or run load exercise 2 from the command line. Here we'll learn all about vias. Zooming in on 2A, this is a basic size error, which is just a width error. You can fix it the same way as width errors by doing an area select and stretch. So I'll just select it from the middle with the A key and stretch. Select the top and stretch up, and that's solved. Now, foundries usually have a different rule called exact size for vias, which doesn't apply in Magic. First, you have to see how vias are created in Magic. For that, go over to exercise 2B. This looks like a bigger via, but it's not. It's actually an area into which contact cuts will be drawn by algorithm when writing GDS. So how do you know where the contact cuts are? Well, there's a command sifc that tracks sif layer names, that takes sif layer names. If you listen to the last lecture, then you know that sif is just another layout format type, and that layers in sif go by names and not numbers. Put the cursor box around the contact and then type sifc_xxx. I purposely chose a wrong name, so I get back a list of known sif format layer names. Figuring out which name corresponds to what layer may require going back to the SkyWater documentation. I've drawn a contact here between local interconnect and metal 1, and the documentation calls those contacts MCON, and indeed there is a layer named MCON in the list. So let's try sifc MCON. Type that in.
Amorphous. After 300 Celsius, you get the anatase. After
now I can see the contact cuts. There are 4 of them in this area, which is as many as Magic could get it to fit in that area. Note that the contact cuts shown are not part of the layout. They're similar to DRC errors in that they represent feedback. There's a command feedback that works with feedback areas, much like the DRC command works with DRC error areas. Feedback Y, for example, tells me what layer is drawn. Feedback clear gets rid of the drawing. Feedback is persistent, so it won't go away until I tell it to go away. Now go back to the single contact of exercise 2A.
a dopant or not.
If you do SIF-C-IMCON here, you'll see that it just barely fits one contact, depending on how much you stretched it to resolve the width error. But what happens to the contact cut if the area is really too small? So you'll stretch, first I'll do a feedback clear to get rid of that area. Now, stretch the contact back until it violates the width rule again. So I'll select and move. There, I got the error again. This time, instead of a contact cut, and then do the SIF-C-IMCON command again. And this time, instead of a contact cut, you got a feedback error. Type feedback Y, and it tells you that there's not enough room for a contact cut. So I'll go stretch the thing back out until the DRC error goes away again. The feedback doesn't go away, as I said, until I clear it, which I'll do now. Feel free to play around with this to see how contacts are drawn inside different shapes and areas. For instance, I can stretch the area down vertically and see how Magic creates a column of contact cuts. You can try, for instance, making a box and see how Magic's algorithm stretches out the spacing between the contacts to make sure it can fit a contact cut in each corner. So this is what a column of contact cuts looks like. Do SIF-C-IMCON.
In this case, is
sorry, and what are the axes? What is the x-axis and the y-axis?
Is there a...
Going on to exercise 2C. Here's a contact cut by itself with no metal surrounding it. Note that for this type of contact, there are no errors related to local interconnect, but there are two different surround rules related to metal 1. The first of these is that there needs to be a minimum of 0.03 microns of metal 1 everywhere around the contact. That's easy to fix. Select the contact with the S key and then type boxgrow C 0.03 UM. The letter C is for center and means grow in all directions at once. From there, I can paint metal 1 by command or by finding metal 1 in the icons and clicking on it with the middle mouse button.
These atoms are going to bounce
Now, there are still DRC errors which say that the overlap additionally must be 0.06 microns in one direction. We already added 0.03 microns, so we need to add 0.03 more, but only in one direction, which doesn't actually mean one direction, but both directions, either horizontally or vertically. Let's say I'll extend it horizontally, so I'll do box grow east 0.03. But let me first select the area of metal 1 around the contact.
It's usually because of a long table associated with
Like
a
so.
crystal structure or a crystal face. So for example, that peak, it means that you have a
And
cube
then do
instead
box
of a
grow
pentagon.
east 0.03 microns, and then box grow west 0.03 microns, and then paint again. And now I'm satisfying all the surround rules. Note that all contacts, except for those involving local interconnect, will require specific surrounding material on both contact layers, not just one. There's a way in Magic to automatically generate a via, so you don't have to do all that box manipulation to get the right surrounding material. It's part of the wiring tool. If you click on the space bar, you'll see the pointer style change, and Magic will say it's switching to a wiring tool. Hit the space bar more times and you'll toggle through several more tools before cycling back to the box tool, which is what you're used to working with. Now go back to the wiring tool and click the metal 1 square. Now I can draw a wire interactively by clicking on the left mouse button. But if instead of just clicking, I hold down the Shift key while clicking the left mouse button, Magic will draw a contact and then move up to the next metal layer, all automatically. I can keep doing this until I get up to metal 5, the topmost routing layer. After that, I can do Shift plus the right mouse button, and it will go back down to local interconnect, the lowest routing layer in steps. In steps. So metal 3, metal 2, metal 1, and now down to local interconnect, which is not really a routing layer, but at least something you need to connect to. Note that going up and down was not symmetric. Magic prefers to continue at the width of metal that it was last using. But when going up layers, it always has to satisfy the minimum width rule, so the metal width always keeps growing as needed. But when going back down, it will stay at the width of the previous route. So with SIF-C, you can see that for the same width of metal, you can get a number of different contact cuts. So I can, if I do SIF-C MCON, I see I've got 16 contacts there. For SIF-C via 1, I've got 25 contacts. For via 2, 16, via 3, 16, and for via 4, there's 1 contact.
See the crystalline structure that the other process is same, the concentration of their precursor of the solvents is different. In this case, no, I cannot find their...
Moving on to exercise 3, load it the same way.
This is not good for my work.
Here you can see 2 more types of errors that I discussed early on in the lecture, one for the minimum area rule and another for the minimum hole rule. Fixing the minimum area rule is straightforward. All you need to do is find some room to add enough extra metal of the same type to meet the minimum area requirement. If I select the metal 4 in the layout and type question mark to find the reason for the error, it says that the metal 4 minimum area must be at least 0.24 microns squared. To find out what the actual error is, use the B key or the box command. The first line of output gives you the box coordinates in microns, and the last column of the output gives you the area. From that output, you can see that the area is 0.2 microns squared, or just shy of the area requirement. If I zoom in and extend the box a little bit in any direction, I can make the error go away. The most common reason for a minimum area rule violation is contacting up through multiple contact types. A wire route will pretty much always meet the minimum area rule, but if you, say, go from local interconnect to metal 2, then there's nothing on metal 1 except for contact and its surrounding material, which isn't enough to satisfy the area rule. So let's say create a local interconnect line, height 0.17 microns, which is the minimum. I'll draw the first part of the wire as a box to start. And I'll do that with box size 0.17 microns, 0.17 microns to get the minimum width, and then paint LI. And then using the same wiring tool and methods I showed you in the previous exercise, I'll type the space bar to switch to the wiring tool. The mouse pointer changes from the crosshair to the arrow cursor. I'll left-click the mouse on the wire to select it. Now I can extend the wire outward, adding new segments by clicking the left mouse button. Now I'm going to do the same thing as in the previous exercise, but I'm going to shift-click on the left mouse button twice in a row to contact up from local interconnect all the way to metal 2. Now there are several errors here, mostly surround rule errors that you should know how to fix now, but the one I'm interested in is the area rule. There isn't enough material on metal 1 here to meet the minimum area requirement. The rule says that the minimum is 0.83 microns squared. If I put a box around the metal 1 area, it's 0.08.
In the house, for example, the division,
or again, just shy of the limit. So again, I can add a bit of extra metal 2 here, and the error should go away. We won't worry about the other errors, which you can fix if you want. But moving over to the minimum hole rule, note that there is no error showing. That's because because calculating a minimum hole area is a compute-expensive process, relatively speaking. And I mentioned in the lecture that those kind of rules will get magic bogged down with a lot of lag. So the default set of rules computed for interactive DRC contains just the ones that you're most likely to encounter during layout. But it's important to remember that that's not a complete set of rules, and occasionally you'll want to check the full set. If If you're working on a small layout, it's okay to switch to the full rules as long as the lag isn't bothersome. To switch styles, I'll go to the menu and select DRC, DRC Complete. Just switching styles doesn't trigger a recheck, which could be time-consuming. So if you want to make sure that the whole design is rechecked with the full rules, then run the command DRC check in the console. Now you see that there's an error marked, and querying it tells you that the minimum area of holes is 0.14 microns squared. Now, it's not possible to select a hole in Magic, so I'll have to zoom in on it and manually set the box to match the size of the hole. The B key tells me that the hole area is 0.07 microns squared, so yes, it's too small. Fixing it means manually creating a larger box and then checking the box size until it's larger than 0.14 microns, or just erasing more and more metal around the hole until the error goes away. So by cutting away metal from the perimeter of the hole, I can fix that error. At 0.16, that's enough, and I erase it and the error goes away. Since we're working with small layouts for the exercises, just keep the DRC style set on full for the rest of the exercises. If you quit and restart Magic for any reason, just remember that it's always going to go back to the default set of fast rules.
The thin film, their titanium dioxide, and no exposition of their UV, and I can determine what is their process of the inactivation. This is their some results obtained of the different pH of the weather with the bacteria Escherichia coli, and absolute is their no exposition with the UV light. UV is the only exposition of the bacteria with the UV, and their titanium dioxide is the fruits of
Moving on to exercise 4.
UV with the thin film titanium dioxide.
Here we'll learn all about wells and taps. It's particularly important that you have the DRC style set to full because most well checks are compute intensive and not part of the fast checks. Over on exercise 4A, we get the most basic well error that wells must contain a tap. That means that an end well is an electrically isolated region and must be contacted to something or else it will be floating and have an unknown potential. Note that there's a P well beside it, and that's not flagged with an error. That's because there isn't actually such a thing as a P well in this process, at least not when it's not in a deep end well, but just sitting in space as it is here. Used like that, it's just another way to represent the P substrate. There's no absolute requirement for tapping the substrate, although in practice you'll want an equivalent contact for the substrate as for wells. So how to get rid of this error? First, you need the tap. N-type material in an N-well in Magic goes by the name N-substrate N-diff, and you'll find it partway down the list in the icons here. So paint some of that into the N-well. Well, that didn't do much. Why? Because the rule actually insists that the tap be connected to something, meaning it needs to contact up to at least local interconnect. Now, the rule really should be saying that the tap has to be connected to a valid potential, but that's difficult to check without extracting the whole circuit, which makes it an electrical design rule, not a simple geometry rule. The compromise made by the foundry was to check for the contact and just assume that if there is a contact there, it's getting connected to something. The contact type is N substrate in contact, so I'll draw that as well.
For their treatment of the domestic weather in the chat, what is the objective?
Now that gets rid of the big error area inside the whole N well. I've created a bunch of other DRC errors though, but those are all kinds of errors that you already know how to deal with. These are all overlap errors. There's N-well overlap of tap, so extend the N-well out to meet the requirement.
If you could explain that table again, I didn't really, or it was the bar graph, the one before that,
Then the tap has to surround the contact by at least 0.12 microns, so stretch that as well, which I'll do by command by that box grow center by 0.12 and then painting in the substrate type. That causes more in-well surround errors, so I'll go fix those again.
The bacteria, for example, in this case, in these graphics,
Now the last error is that local interconnect has to extend beyond the contact, so I'll add extra local interconnect on the ends.
But here each point is a bacteria colony.
yes, in this case, it's around their
And now I fixed all the errors. Moving on to exercise 4B, I've already put the tap contact in the end well, but I've also put a substrate contact in the substrate here, and now I'm getting more errors. Checking the error, all taps must be connected. So, as I said, there's no specific rule that says substrate has to be tapped, but once you have tapped it, that tap has to be connected to something. That rule is exactly complementary to the end-well rule. It wants to see a contact along with the tap. So I'll do the same thing I did in the last exercise, but this time I'll find P substrate P contact and paint it in the middle of that area, and then resolve the various surround errors. Note that because the P-well layer is not really a well here, there's no requirement on how much it needs to extend beyond the tap, so a distance of 0 is just fine. I'll go ahead and box grow 0.12 microns, paint more of the P substrate, and now I'll have to fix the metal error, and there we go. The deep in-well in exercise 4C is a complicated structure. The deep in-well itself is just a buried layer, and it's not allowed to float, which is why it's got errors around it. First, there's a width error, which is easy to fix. The area is not quite big enough, so I'll add a micron in both directions and make that one go away. So I'll stretch east by 1 micron, and then I'll stretch south by 1 micron. There's also a spacing error. Deep in-well spacing to in-well is less than 4.5 microns. The distance in-wells need to be from deep in-well is huge, and they can interact at quite a large distance. In this case, it's not flagging the error at the position of the in-well, but the in-well involved is the one back in exercise 4B. To get rid of that error, I'm going to do an area select on the whole exercise 4C and move it out of the way.
In this case, I need use the solar light. The solar light is a physical light, and what is the process? Modify the bandgap that I can use.
Now I have only one error, which is basically saying that I have to have a wall of in-well around my deep in-well, both to contact to it and to isolate the P-well region in the middle of it. The error feedback extends to all areas that need in-well, so without paying attention to the distances, I can just paint in-well over the error areas. I'll start in the lower left corner and extend the box to cover the error area and paint in-well over that region. But that seems not only not to have fixed the error, it has caused another error as well. But I know that I need a ring of in-well, so I'm going to treat in-well like a wire and use the wire tool to go finish the ring all the way around like this.
But the titanium dioxide is using UV.
Yes, using UV.
At first it might appear that I didn't solve anything because the error feedback is still there. But if I query it with the question mark, I see that the error changed. Now it is showing a different error, which is one that we've already seen, which is that all in-wells must contain a metal connected tap. I can solve this one just by putting a well contact anywhere in the well. The contact can be over the deep in-well layer. The only place it can't be is in the isolated P-well region in the middle. But generally, if you have a deep in-well structure like that, you want it to be completely tied to a known potential by a complete guard ring around it. That goes all the way around. For that, there's a menu item. But I'm going to go ahead and finish this first, showing you that the error goes away. See, the error already went away. And I have a little bit of gap that I need to stretch out to solve that DRC error. Okay. And on the top too. Now I've solved all the errors, but I'd rather have one with a full guard ring around it. So for that, there is a menu item. Select menu item devices 1, deep in-well region. To see how that works, make the cursor box into an area larger than the in-well for exercise 4C. Now select the menu item devices 1, deep in-well region. You'll see that you get everything drawn for you: the deep in-well, the in-well fence around it, and the full guard ring surrounding it. The only thing left is the big error block, and if you look at the reason, you'll see that deep in-wells have to be kept even further away than deep in-well to unrelated in-well, over 6 microns away. The bottom line is that deep in-wells are expensive area-wise, but as I said in the lecture, if you need the noise isolation, then it's worth it. And we'll just select the whole thing and move it out of the way, and that resolves all the errors again. Next up is exercise 5.
Cost-effective way to make a bunch of this titanium dioxide stuff where it might be better than just blasting it using.
It could be. Perhaps you can make a filter that is transparent. So
there aren't any DRC errors showing in this layout. Here we're going to look at the derived layers that Magic creates and how they can become issues for DRC, and how the actual error and the solution to it may be harder to see because the layer isn't shown in Magic. In exercise 5A, this looks like a standard transistor configuration with poly crossing diffusion. However, if you select the transistor layer in the middle and type what, you will see that it is NMOS LVT. Draw a transistor below the one above using the same 2 layers as drawn in that one, like this, with poly and diffusion. You'll see that Magic replaces the intersection of the 2 layers with a transistor type. If you select that and type what, it says that it's a plain NMOS. There are default composition rules in the tech file that say that when you draw poly over in diffusion, or vice versa, you get type NMOS at the intersection. To get type NMOS LVT then requires that you specifically paint type NMOS LVT into that area.
It's going to be like
some GDS layers are just the same as the Magic layers. Magic doesn't auto-generate everything, just a few key types like implants and contact cuts. So I'll do that command again, SIFC-XXX, to get that list of known types. The ones that are the same as the drawn layers are going to be diffusion and poly, which in the list are diff and poly. So I will do the commands SIFC diff and SIFC poly. These are a bit difficult to see, and you might want to hide the actual layers in Magic to see what the feedback results are, since they're in the same colors as the layer. So what are the implant layers? First, there's the N and P implants. Those are called NSDM and PSDM. So SIFC, over here in the list, NSDM and PSDM. So typing SIFC NSDM shows you that the implant layer surrounds the diffusion and has to overlap it by a certain amount. This can never be a DRC error in Magic because Magic enforces the surround rule in its auto-generation recipes. SIFC PSDM shows the same thing on the tap region. The tap is always the opposite type of the diffusion for the diffusion in the same well or substrate region. Now, what makes an NMOS LVT an NMOS LVT and not an NMOS? Well, it's the LVTN implant, which is a threshold adjustment, and if you do SIFC LVTN, you'll see it around the top transistor, but not the bottom one. Looking next door at exercise 5B, the only difference seems to be some broken stripes, lines around the diffusion. If I select the diffusion and type what, I see that it's type NVNDIF, which is the high voltage tolerant diffusion. The transistor is then necessarily a high voltage type, which is NVNMOS. What makes a high voltage transistor a high voltage transistor? It's the HVI implant, which stands for, obviously, high voltage implant. CFC HVI will show you where the implant is. Compare that to NSDM, the HVI layer. It extends a bit further out. So if I clear that and look at NSDM, it goes out that far, and then if I look at HVI, you can see it's a little bit further out. Most rules pertaining to the HVI layer will show up if you try to mix high and low voltage types. So for example, draw some regular end diffusion above the high voltage end diffusion and connected to it. So I'll go up to the top here, zoom in on this area, and I will draw some regular old end diffusion there, and it immediately shows an error. So you'll get a DRC error that says you have to keep space between high and low voltage diffusions. Since the error is related to a derived layer, the error you get is reporting a value that doesn't appear in the Foundry documentation, but it's a combination of several rules. In this case, the rules are diff-tap 23 and diff-tap 22. You can go find the rule documents and confirm for yourself that the distances of those two rules do, in fact, add up to 0.36 microns. You'll note that the HVI layer does not cover the tap contact. This is technically not a big issue because, unlike an N-well, the substrate is grounded and will never see a high voltage. But there is a high voltage substrate contact type. You can paint over the contact with the high voltage tap contact type, and you can paint over the diffusion with the high voltage tap type.
The other one magnetics and the other one electronics.
So we'll go find the MV substrate contact.
Devices.
And then over this area, we'll paint the MV substrate diffusion.
Well, for the, I guess, yeah, for the chip design team part.
So then doing CFC HVI shows the whole area, including diffusion and tap, covered by the HV implant. Note that the minimum surround of the tap and the diffusion would, in fact, produce two separate areas of HVI that would have spacing violations between them. Again, Magic's auto-generating recipes will close up gaps like that and resolve such spacing errors automatically. Over in exercise 5C, we have a similar situation. Polycontacts require a special type, not an implant but a layer etch, called nitride polycut, or NPC. The NPC etches through any nitride residue on the poly to ensure a firmer contact between the poly and local interconnect. Just looking at the topmost contact, doing CFC NPC will show you where that etch is made. Now go down to the second two shapes. Like the HVI layer we just looked at, this arrangement of polycontacts causes the NPC layer recipe to bridge between the contacts to avoid the spacing error. Now the two contacts below that get trickier. It's really hard to figure out how to bridge between two shapes positioned diagonally from each other. CFC NPC will show you that the automatic layer generation creates an extra bit of material between the two shapes, a little extra bit of mask geometry between the two contacts. This is positioned such that it satisfies all width and spacing rules for the NPC layer. Below that, it's not entirely clear to me why the added material is in a different arrangement here, but it continues to satisfy all width and spacing rules, and there's no Foundry rule prohibiting the NPC layer from overlapping diffusion or diffusion contact, so this arrangement should be DRC clean.
Nickel might be one of those materials that require magnetization before you measure. Okay. So measure the material, show me the result immediately. Don't try to measure all the materials. Measure one, show me quickly, like a snap picture, and we will decide if we need to magnetize it or not.
Okay, so with the thing, like start with I will measure the
Going on to exercise 6.
Yes. Well, have you received the pellets already? Okay. Because that's what I
When
would
you
like-
load exercise 6, you're confronted with 3 apparently empty squares with errors marked inside them. These are subcells, and Magic's default behavior is to start with all subcells unexpanded, which is to say with the contents hidden. To expand all subcells in a layout, put the mouse pointer somewhere over the background and type S for select. This selects the bounding box of the top level cell in the layout window. Then type X to expand. These layouts are large, so you'll need to zoom in on the first one to even see the example title. Here we're looking at parameterized devices, which is to say devices that Magic draws automatically, or which are fixed layout devices from the Foundry, so you aren't supposed to even edit them yourself. The first one is a simple parameterized cell. This is an NMOS FET device created from the Devices 1 menu with all the default parameters. The question to ask is, if this is a device that Magic drew, then shouldn't it be DRC clean? Why is it showing errors? Well, let's look at what those errors are. Querying the error says minimum metal 1 minimum area is less than 0.083 microns squared. That's a metal minimum area error, and we know how to deal with it. But why is it there in the first place? Well, Magic could avoid this error automatically, but that requires adding more metal 1 to the device. And Magic would have no idea what the designer's intent was, so it might end up putting the extra metal in the way of something else, making it harder for the designer. But what is certainly true is that those contact points have to route to somewhere, so they're going to have extra metal attached to them anyway. So even though the error itself is in a subcell, it gets solved the same way. Just add some metal 1 over each poly contact.
But yeah, see if it not open up.
Like so. So I'll put metal 1 on top, and I'll put metal 1 on the bottom.
Yeah, but I need to have...
And the error has gone away. Now descend into the subcircuit, which you do by putting the pointer over the cell and typing I for instance select, and then the greater than symbol, which we'll treat like an arrow indicating that we're pushing into the cell to edit it. Inside the cell, the extra metal is not there and the DRC error still exists, but pop back out with the less than symbol, of course, and the error is gone. So that's how DRC errors in subcells can be resolved higher up in the hierarchy. Now go over to exercise 6B. This is one of those truly difficult situations. The device is an ESD FET designed for surviving high voltage, and it actually purposefully breaks existing design rules. For example, it has a transistor gate at an angle where the rules, if you look them up, say that transistor gates are absolutely not allowed to have angled edges. To be blunt, Magic does not believe in rule exceptions, and frankly neither do I, but a rule exception doesn't necessarily mean that the rule that it is accepting is necessarily wrong. It's more accurate to say that the rule is oversimplified, maybe because a completely accurate description of the rule would be impossible to describe by a DRC engine. Regardless, Magic doesn't know how to prevent this DRC error from showing up. There's really only one way to deal with this in Magic, one way to make it ignore the contents of a cell that is known good but breaks some DRC rules, and that is to abstract it. In the OpenPDK's installed PDK, abstract views are under a separate directory in each library called maglef. Those are left-like views, and that's actually not what's needed here. Actually, all library views are abstract in a way because they contain pointers to GDS files, so that what shows in the layout view is not necessarily more than Magic's best representation of the GDS data. But you can change the layout in all sorts of ways without affecting what would be written out to GDS. This is dangerous, which is why its use is limited to library cells that are read-only and which are carefully prepared from vendor data. But we can use the method to our advantage to make a cell appear DRC clean so that it doesn't show up as false positive errors in a layout. Select the cell with the I key, and you can see the name. Now type cell name file path, and then give it the name, which I'm going to, instead of typing in, I'm going to do by cut and paste from the console window. And that tells you where the cell is located. I want to relocate it locally because the original library view is read-only. I could copy that file from the location to here, or I can just do this now, which is to repeat the cell name command, but change the file path by adding a dot at the end. And that changes the file path to the current working directory, and follow that by pushing into the cell with the greater than key, and then issuing the command save to write that to disk. Just to be sure that I can do anything to this cell without affecting the data that gets written, I'll run the command property and make sure that, yes, it is pointing to a valid GDS file. If I wrote GDS of this whole exercise, I would get the real cell contents, not the contents of the abstract view, which is what I want. So now I can modify it to make it show as DRC clean. I'll do that by erasing all of the angled sections of polysilicon, mostly by erasing polysilicon wherever it's angled. In fact, doing that also makes the device extract properly because the extraction model doesn't account for the flanged gate ends, but if Magic extracted the original device, it would try to incorporate those angled edges and come up with a slightly different width, length, or both. So this modification fixes both the DRC false positives and the device extraction. I'm going to do this mostly by zooming in on the poly areas and erasing poly. So erase poly on that end. This end. Go to the bottom. Erase poly out of there. These ones I can't erase poly, but I can just click on the diffusion type. That will erase the poly. And then do the same thing here. Erase poly.
Plastic.
And over here. And now it is DRC clean. So now I'll pop back out to the exercise. The third example in exercise 6C is similar to exercise 6B, except this is an example of a fixed layout device that is in the primitive device library instead of the I/O library. But it is essentially the same. There are geometries in the cell that are prohibited elsewhere, and so DRC errors are necessarily flagged. Some rule violations in this cell have to do with 45-degree angles, like in the last example. The rest of them have to do with the deep in-well. Hint, you don't need the deep in-well in the drawing. There are ways to represent an isolated substrate that would make the device extraction work without it. Don't worry about the device extraction for this exercise, though. Once you have 0 DRC errors in the layout window, then you can move on to exercise 7.
You enter the lab. Here is the table for the BSM. And there is a panel, like a shelf. In the bottom of the shelf, there is a big metallic base with some extension arms that you can use to hold things in place.
Here we're back to simpler things than just messing around with the file paths and abstractions, just picking up some of the miscellaneous rules associated with the process. Some of the exercises are in subcells, so like before, select the top level and expand. As I mentioned in the lecture, Magic has an underlying integer coordinate system that is the same as the manufacturing grid, making it awfully hard to draw geometry that is off-grid. If I zoom way in and make a box as small as I can make it, then I query that box. I see that it is 10 nanometers by 10 nanometers. This is still twice the manufacturing grid. To get it smaller, I need to type snap internal, and then I can make the box 1 by 1 or 5 nanometers by 5 nanometers. So I can make this half again as big, and it's now 1 unit by 1 unit or 5 nanometers. To make the box any smaller, I'd have to scale down Magic's internal grid. I could try that now by doing scale grid 1, 2, which, if it worked, would cut the grid down from 5 nanometers to 2.5 nanometers. But Magic won't let me do that. It notes that the scale I'm requesting would be finer than the minimum manufacturing grid, so I'm prohibited from doing that. Other tools will let you cross a non-Manhattan polygon with another polygon that creates an off-grid intersection. Magic won't even allow that. The easiest way to show that is with a triangle with an odd-numbered size. So I'll do box size 2929 and then split paint southwest metal 1. That draws a triangle. Triangles are naturally bad, so I'll add material behind it to make it DRC clean, like so. Now I put the cursor box around that and type A to select all or select area, and then do copy east 100, then flip it with the command side. Now if I move it back by an odd number, then the angled edges should intersect at an off-grid point. Let's see what happens. I'll do move west 65 and zoom in on that supposed off-grid point. Look at what happened. Magic couldn't generate a point off-grid, so it ended up legalizing it in a way. Now, below that area is the one way you can get an actual off-grid shape, showing the same type of geometry I just made, but then putting the shape in a subcell, flipping one of those subcells, and moving it back an odd number of internal units. Querying the error that occurs, you'll see that it says that this position does not align with the manufacturing grid. Now this is truly hard to do, but it's good to know that if you manage to do it, Magic's DRC engine will catch it. The solution is just to move one cell over by one internal unit, which I can do with the keypad. Because only 45-degree angles are allowed, then no off-grid error can be more than half a unit out of alignment.
So the calculation of the area is wrong. But if you start in a circle, you're going to have a circle.
Speaking of 45-degree angles, over in exercise 7b, we have one such error. Querying the error, I find that the rules say that you can't have any angles at all on local interconnect. There's only one way to solve this, and that's just to paint over the angled corner, which I'll do with the middle mouse button from this position here. Going across to 7C, this one looks okay, but if I query it, Magic seems to disagree. These things can be very hard to see by eye. If I select the corner of the shape, the box command tells me that the shape in internal units,
So the idea is your capacitor.
so query with box,
Okay. Both sides.
and I can see that it is actually 201 by 200. So it is not exactly 45 degrees, and that's an error. So I can fix this one with the command box grow north 1, erase,
Yeah, I mean, like,
and then split paint southwest metal 1.
yeah, you do.
The erase is to make sure that I don't get artifacts of painting over an edge with an edge at a slightly different angle, which can make quite a mess in Magic. Since I made the box taller, if I zoom in on the corner, I can see I've created a width error, but that's easy enough to fix.
The same layer. They don't have the same layer.
Print something that can be adjusted.
These two can have the same layer.
So I'll just add some,
But I know, obviously.
add a little bit more than that, and that error goes away.
Yes, you put the paper.
Moving on to overlaps. In exercise 7D, if you recall from a few exercises back, if you draw poly over diffusion, you get a transistor. But what if, like the first exercise on this page, you put the poly in one cell and the diffusion in another cell and overlap them? Well, what you get is an overlap error. There's no easy way around this. Magic just doesn't allow it. It can get really hard to detect these things in GDS files written out by other software because object-based editors may allow this kind of thing. Extracting such a thing is problematic too, which is one reason that Magic prohibits it. If I poke around this device, I can see that the diffusion is drawn in the top level cell and the poly is in a subcell. The best solution here then is just to paint poly over the poly area and then preferably to delete the subcell, since at best it's going to give you more overlap error messages during extraction, even if it extracts correctly. The transistor was an example of a prohibited overlap. Contacts are a different problem, with a corresponding rule called exact overlap. It means that contacts are not prohibited from overlapping between subcells, but if they overlap, they must overlap exactly. That's due to the automatic generation rules for contact cuts. If you put the box over the top figure in example 7e and type SIF-C via 2, this one looks okay. Unfortunately, looks are deceiving here. The SIF-C command works on a flattened layout to show you everything under the box, but by doing so it misses things which might end up differently due to hierarchy. In this case, the figure is made from two overlapping cells, so there is hierarchy involved. Note here that in the SIF-C view, the vias are in the optimal position, overlapping exactly at the corner. To do that, Magic shifted the position of one of the contacts relative to the other three. Now push into that contact cell. In the cell, also do SIF-C via 2.
What?
See the problem? Within the cell itself, the contacts are aligned equally, but back in the top level cell, the contacts would have to be arranged differently for the GDS to end up error-free. Therefore, it's flagged as an error. There are only a few things that can be done with this. One is to flatten it. So if I put the box around the whole thing and type A for an area selection, that's flattening the cell contents into the selection, which is itself a cell. Now I can type, say, copy east 3 microns, and I get a copy of the flattened geometry. Nothing is overlapping, so there's no DRC error. SIF-C via 2 on this shows me the same arrangement of cuts, but that is actually the way it will be written out to the GDS file. Now below that, there's another via that shows the other way to get around the issue. That figure is also made with two overlapping cells. But if I select one instance and copy it down below, I can see that the contact areas in this cell have been split, effectively making a square contact at the end. It's a square, so Magic can't adjust the cut there. The cut has to go in the middle of that contact area. I can copy that cell again to somewhere off to the side, and then do rotate 90.
Yeah, I guess.
And
Another group.
overlap them.
They're trying to find maps too. It's like, who's your advisor? It should be.
So where they cross, I'm overlapping contacts illegally.
You're going this way. No, I'm done.
But if I move the shape so that the square parts at the end overlap exactly, then I have an exact overlap, and that's legal.
Oh, wait.
So
can I
it's
stay here for a sec?
yeah. So I'll move that now so that it's
Until
those are exactly overlapping. Whoop, just passed it. Go back.
Bro, I feel so bad for these videos.
There.
Cause like,
So it's not that you can't cross contact rows or columns, but you do have to draw them in a particular way so that they satisfy the exact overlap rule.
I'm not sure.
Now, if I do SIF-C via 2 here, it looks the same as the first example.
I felt bad too. My alarm kept on sounding like pretty loudly. There's no way to just make.
So there won't be any confusion about what's written to GDS.
Probably is. I don't know how.
Knowing what this cell looks like, I can now figure out the error in the second figure. The squares at the end aren't exactly overlapping. So I'll just select one aside and keep moving that toward the other until the error disappears.
Yeah, like I left like really late.
And then I know I have it overlapping exactly.
They're everywhere. And not okay. So change the video.
Let's move on to more advanced stuff. Before, we looked at abstract views, which can be used to avoid having magic generate DRC errors for things that create rule exceptions. Those cells, although they showed DRC errors, would still both extract correctly and generate GDS correctly. But sometimes there are special sets of rules that are so far off from normal that there just isn't any reasonable way to deal with them except by abstraction. The seal ring is one such example. A seal ring is a cell that goes around the perimeter of a chip just outside the pad frame, and it is supposed to protect the chip from catastrophic things that happen outside of it, like sawing and dicing. The seal ring is then a physical barrier between the chip and the saw street, and it makes very abnormal use of layers because those layers are designed for a physical use, not an electrical one. So you can get things like contact cuts that are not square but run the entire length of the chip. They break all the rules, and there are some special layers that occur only in seal rings and therefore aren't worth the trouble to implement in the magic tech file. So the PDK for SkyWater has been set up to provide a seal ring generator that generates a correct seal ring shape by procedural script. You can import only an abstract view of that seal ring into Magic. There's actually a separate technology file for Magic that goes along with the script that defines all of the special layers used in the seal ring, and it will generate correct GDS. But you can't read that layout into Magic with the technology. So what you're looking at is, in this example, is an abstract view that is designed specifically to be a DRC-free representation of the seal ring, but in fact looks nothing like the seal ring at all. Basically, it's like a left view with obstruction layers showing that you can't put any diffusion in this area without causing issues. Attempting to paint diffusion over the border stripe results in one of those can't overlap those layers errors. If you push into this cell and then type the command property, you'll see that there aren't even any properties like the other abstract views we've looked at have. This cell is essentially useless by itself. To get the seal ring, you have to use the seal ring generator. Fortunately, that's easy because you only need to know one thing, the size of the outer edge of the pad frame of your chip. If I pull up another terminal, I can run the seal ring generator from anywhere. Just run the command from the Linux prompt. So from VSD DRC lab, I'm going to type user share pdk sky130a libs.tech magic seal ring generator sky130 gen seal ring.py. That gives me the usage information. I'm going to run that now, giving, say, 2,000 microns for the width and height, and a name seal_test for the target directory. So I'll back arrow to get that, add 2,000, 2,000 for width and height, and seal_test for the target directory. Since this script is all a self-contained seal ring generator, it runs Magic in batch mode, and everything is done behind the scenes. The result is put in the target directory, so if I run ls on that now, I can see that I have 2 layout files, .mag, and 1 GDS file. You saw the second of those layout files in the example, and as I mentioned, it is not usable as is. The one you would want to use in the layout, as instructed by the script output, is the other one. There's an issue, though, that Magic has already read in a cell seal ring corner abstract from a location that was specified in the lab exercise, but which Magic doesn't normally have access to. And that has the same name as the new cell that was just generated. So to look at the generated cell, it's a better idea to start a second run of Magic. Since I have that run Magic script, I can just run it from the terminal's command line. Run Magic. Then in the Magic layout editor, get that right to the size of my window. Then I want to make sure that Magic can see the directory where the seal ring layout is by running the command add path seal_test. Then I do load add adv seal with a capital S _6um_gen. This is what you see, a 2x2 array of the seal ring corner abstract layout. If you expand that using the S key and the X key, you see that the corner has been expanded and rotated to create the complete seal ring. Unlike the corner abstract cell, if you type property in this cell, you'll see that it points to the GDS file in the same directory. Because the GDS file reference is in the top level cell, nothing below it, that is the corner abstract cells, has any impact on the output GDS. The output GDS will be taken from that file and nothing else. To see how that works, there's a separate launch script for Magic in the repository called GDS_Magic. From the terminal where you created the seal ring, you'll want to run that. This runs Magic with a different tex file for the SkyWater process that represents most of the GDS layers exactly, much like other layout editors would, but it doesn't contain any information about DRC or extraction or connectivity, so it's useful mainly just for looking at GDS files. Since it's a different environment from what we have in Magic right now, just quit out of Magic here and we'll run the launch script now. So exit from here. And then in the terminal type GDS_Magic. When Magic comes up, make sure the cursor box is in the layout window. Let me adjust it to the size of the screen. And then run the command GDS read seal_test / ADV seal_6um_gen. If you looked at the terminal output while it's reading, you'll see that even this tex file doesn't encode all of the GDS layers defined by SkyWater. There's still some undefined layers, mainly because Magic isn't really designed to work with layers like this, and it runs out of planes to use for the layers. But with most of the common layers present, you can zoom in on a corner and see what part of the seal ring looks like, which is basically nothing like the abstract view. For one thing, there's tap diffusion defined at a 45-degree slant, which is prohibited by the rules, and tap without contact, which is prohibited by the rules. You've seen both of those rules before. So there's not much to do with this view of the seal ring, and you can quit this run of Magic, but that shows you a way that you can see the underlying GDS layers in Magic. You can also use KLayout, which is an object-based layout editor, and we'll show you everything in the file. Moving along to exercise 8b, we see another example of a cell that has layers and rules that are simply unimplemented in Magic. This one is treated exactly like the ones in the earlier exercise, where we used abstract views to remove the DRC errors. This one, like those, will extract correctly, but unlike those, it has many special layer types that are not represented in Magic, and so it can only be used as a type of abstract view. This is what is known as a read-only cell. If you push into this cell and type property, then you will see that it references a GDS file. And if you write out a design to GDS with this cell in it, the GDS contents will be pulled from that file, not from the Magic layout view. You'll also see that there are close to 200 errors in this file, although you may need to run DRC check on it to get them to show. With the DRC full style there. It is interesting to look through these errors and see just how many normal rules are violated by this cell. These are not special rules per se. They just have knowingly violated rules to compress the size of the SRAM cell to as small as they could get it. Why does it work in spite of all these rule violations? Well, mostly because the cell is designed in large arrays, and the fact that every device has the same geometry surrounding it means that you can get by with more conservative rules without affecting process yield. Going on to exercise 9. Exercise 9 demonstrates what a latch-up rule is. When you load this file, you'll see that it is just a few standard cells, and that with the full DRC check, the whole thing is covered with errors. One of those we've seen before. All in-wells must contain metal-connected N+ taps. So we know there needs to be a tap diffusion somewhere. The other errors are NDiff distance to PTAP must be less than 15 microns, and PDiff distance to NTAP must be less than 15 microns. This is sort of saying the same thing, just as a stronger requirement. Not only must wells have a tap contact, but they must have enough tap contacts that every bit of diffusion in the design is within 15 microns of one of those tap contacts. That's the latch-up rule, and it's designed to make sure that the well and the substrate are pegged well enough that they won't vary from their expected voltage and cause trouble. This being a standard cell, it's supposed to be handled automatically by place and route tools, and that means that there should be a tap cell that is part of the standard cell set, and in fact there is. If I select one of the cells, I see that it's part of the SkyWater FDSCHD library. Now, we're doing this by hand and not by place and route tools, so I'll have to tell you what the tap cell name is. You can get it using the get cell command. So put the cursor box around the end of the layout and then type get cell sky130 underscore FD underscore SC underscore HD underscore tap vpower vground underscore 1. If I place it right, then the large error areas disappear immediately. I'm a bit off, so I'll just have to use the keypad keys to position it just right. So a little bit to the right and down. And once it's in position, then all my DRC errors go away. The lesson here is that tap cells are small things, but missing them can cause a large number of confusing errors. We're getting close to the end. Looking at exercise 10. Now we get away from Magic's DRC engine and look at electrical rule checks, specifically the antenna rule check. This is a standard cell design, simple like the last one. What I want to represent is what happens in a large standard cell design, where you have a route that stretches a long distance between two cells. Instead of giving you a huge standard cell design, I'm giving you a few standard cells with a very, very long route between them, which is effectively the same thing. First, I'm going to expand the design. And now an electrical rule check, as the name suggests, implies that some knowledge of the circuit is needed to evaluate the rule. To get knowledge of the circuit needs to be extracted. So the first step in running any electrical rule check is to do an extraction with the commands extract, do local, and extract all. And it's done. Now that the circuit is extracted, you can run the command antenna check. By itself, the antenna check command doesn't produce any text output, just feedback. You can use the usual command feedback Y to find out what the errors are. Unfortunately, those errors aren't too helpful if you're looking for details, but they do tell you where the errors are. If you want details, then run the command antenna check debug, followed by antenna check. Now you get some information, specifically on the antenna ratio that triggered the error. The error is that the ratio of the area of metal, marked by one of the feedback entries, to the area of the gate, marked by the other feedback entries, is greater than 400. In fact, the actual ratio is more than twice that. So there are two ways to solve antenna violations. The first is to tie down the route to a piece of diffusion, which is a diode. If the feedback from antenna check says that the error is at plane metal 2, then you need to connect anywhere from the highlighted metal down to diffusion. There's a special standard cell which contains a diffusion diode, which is the best thing to use for this purpose. I've provided one here, and it's on the end of the layout. You know now how to wire a route and connect and contact down. We only need to go across from the input A, where that route in violation starts, over to the diode next to it. So we'll do that with the wiring tool. So I'm going to click on space to get the wiring tool, click on the metal 1 route, stretch left to get to the diode, then click the left mouse button to paint the route segment, and then click shift plus the right mouse button to contact down. And that's all. Now we changed the electrical circuit, so we'll need to extract again. So be sure to clear the feedback areas first because they won't go away by themselves. Do feedback clear, and then we'll do extract all. Then do antenna check debug and antenna check. So this time there's no feedback and no error message, so we fixed the antenna violation. Now I'm going to cut through that trace that I made, which will cause the antenna violation to pop up again. But this time I'm going to just look at what the route is. To see what the route looks like during manufacturing, just erase everything or hide everything above the metal 2 where the antenna violation occurs. So you can do the command cno via 2, metal 3. You can see from that while metal 2 is being created on the wafer, the long metal 2 line has its end hanging in midair, and that's what makes it an antenna. It's also true that the only thing making it an antenna is that route that goes across in metal 3. In fact, as long as nothing is in the way, I could just as well make that route segment in metal 1, and then there would be no antenna. So let me do that instead. So back to the wiring tool, I'll use the space bar to get the wire mode. I'll click on that metal 2, route up to where the metal 3 route was, click shift plus right mouse button to contact down, stretch across to the other metal 2 line, then use click shift plus left mouse button to contact back up. And we're done. Does that work? Well, let's do extract again with extract all. Then do antenna check debug and antenna check. And no feedback and no errors. So we just solved the antenna violation without adding diffusion to the route, just by changing layers the right way. we're on the next to last exercise, which has to do with density violations. Load exercise 11. The size of this layout is deceiving because labels have been scaled to the size of the layout. This is a very large layout, which you can figure out by selecting the top level cell and doing B for box. The size of the cell has been made exactly 700 by 700 microns, which was chosen because that's the window size specified by SkyWater for the density checks. Since density is something that is only meaningful for a full chip design, there isn't much point in running density checks or fill generation on a small area. These density checks would need to be rewritten to handle small areas. Anyway, looking at the layout, I've chosen 2 layers to represent the problems of underdensity and overdensity, as I described in the lecture. Metal 1 in purple is only a thin ring around the boundary of the area, and so is very much underdensity. Metal 2 in pink is filling up most of the area other than the border, and that is very much overdensity. But let's see how you would check that. The underlying command in Magic for checking density is sif cover. It takes a GDS layer sif name as an argument, so it would be something like sif cover met 1. And if I type that in, I can see that I have a bit over 5% coverage of metal 1 in this design. For metal 2, it would be sif cover met 2. And I see that I have about 86% coverage of metal 2. The remaining metals don't exist at all, and as you might expect, running sif cover on these just returns 0. Now, the sif cover command is useful, but it doesn't say anything about what the limits are or whether or not you're violating them, and it only checks the coverage and the total area of the cell in that window, which is generally not how foundries define the density rules. Density rules are generally computed over smaller areas, stepped in X and Y, and the density has to be satisfied in each of those areas so that we're looking at the density across the whole chip and not just getting a single value for an average. That requires some complicated manipulation of the layout as well as some complicated bookkeeping on the calculations, so it's done by a script. Like the seal ring generator, this script is provided as part of the SkyWater PDK. Since density checks are specifically for mask data, the density script takes a GDS file as input so that it can look at just the mask data. So the first step to check density is to create a GDS file. Do that now with GDS write exercise 11. And now I'll go over to another terminal and I'll run the script, which is, well, first CD back to the VSD DRC lab from the new terminal, and then the script is user share pdk sky130a libs.tech magic check density.py. Without arguments, I get a usage message which tells me that I need to pass the GDS file as argument. So I'll do that again with up arrow to get that command back and type exercise 11.gds. Now, if you look at the results that scrolled by, you'll find that although the computations are much more complicated, it still comes up with the same answers for the metal 1 and metal 2 densities. That's because the size of the layout is the size of one check area, so there's only one place to check and the numbers should be the same. Now, essentially everything here is in error, and as you might expect, there is another complicated script for dealing with it. That script is called generatefill.py, and it's in the same place as checkdensity.py. So I can run that one with the command, same, let's just jump back to that and then change checkdensity to generatefill.py. Note that in this case it's asking for a magic layout.mag file, not a .gds file. So go ahead and pass it the exercise 11 layout as argument exercise_11.mag. Now it warns you that this could take a while. For a complete full chip design, it can in fact take a really long time. The 700 by 700 area is not all that large, but it still has a lot of computations to run, so you can expect it to take a minute or so to complete. So I won't even have time to start telling you anecdotes before it's done. Still, it's a full minute of dead time, so I'm going to skip ahead. The output of the script is a GDS file. Running ls on the directory shows you that a new file exercise_11_fill_pattern.gds got created. To see what it generated, you can load this in the magic session that you're already running. So in the command line, do gds read exercise_11_fill_pattern. Give that a little time to read in and then select it and expand it. This is quite full of fill patterns, as you can see. The fill pattern generator is attempting to satisfy fill requirements for all layers, so it has done everything from diffusion up to metal 5. Take a look at metal 2, for example, by doing C no star to get rid of everything, and then C all M2. No, that didn't show much. The metal 2 fill layers are on a special type called M2 fill, which is not part of the alias all M2. So do C M2 fill. Now you can see that the fill patterns have been made to fill in the gaps in the metal 2. You know that metal 2 was already over full, but the fill pattern generator is not smart enough to know that. It just assumes that layers are underfilled, and it tries its best to add patterns in bare areas to keep up the density. In practice, you want to merge the patterns with the original layout. So load exercise 11 again. I can do C star to go back to seeing all of the layers. Now, getting the position right is very important and should be done like this. Start by putting the cursor box at the origin with the command box values 0000. Then pull in the fill pattern cell and use the option child 00 to make sure that the origin of the fill pattern aligns with the origin of the top level cell. So the command is get cell exercise 11 fill pattern child 00. Now the fill is unexpanded, so select the top level cell and expand again with the X key. Now go back to looking at just metal 2 and metal 2 fill, which I'll do with C no star and then C metal 2 comma metal 2 fill. You can zoom in on, say, the center area of metal 2 and see that the fill is properly centered in the design. The DRC should have completed by now, and there shouldn't be any DRC errors because the DRC is correct by design when generated from the script, which encodes and enforces all of the metal width and spacing rules. So if in this layout I do SIF cover metal 1, now it takes a lot longer to compute because it has to look at all the fill shapes, but what you see when it's done is that it is still 5.6% because metal 1 does not include the fill, which has a different GDS layer name. Unfortunately, I can't use lists of layer names with the SIF cover command, but there is a special style used by the density check and generation scripts that does this. It can be reached by typing the command SIF ostyle density. Now if I do SIF cover met1, it tells me that there are other names to use. These layers include all mask geometry for a layer that has a density requirement, so such as do SIF cover, and we'll use M1 all. Again, this takes a bit of time to compute, but when it's done, you will see that you have, wait for it, 58% coverage, which is good and within the limits. So I can do the same thing with SIF cover M2 all. And again, wait for it to finish. And you'll see that M2, however, gives me over 92% coverage, which is way out of bounds. As I said in the lecture, there's not much you can do about overcoverage except to try to eliminate metal in the design. That can't be automated. This is, of course, an example only for demonstration, and in practice, you would never make these giant areas of metal 2, and really in practice, it is very difficult to end up with too much metal. Likewise, typing SIF cover M3 all, which again will take its good time to finish. But it will show you that in the absence of any drawn geometry, the fill generation script is aiming for a specific amount of fill, and that is right around 50%. If you zoom in on the metal 2 fill, you'll see how complicated the fill generation algorithm actually is. It's generating fill in different sizes and working through several passes with different sizes and distances of fill shapes. If you want the official final result, you will need to generate GDS from this combined layout with the original design and then the generated fill, and then run the density checker on that. That takes considerably longer than running checks on the original, mostly empty design, so I'll leave that as an exercise for you. For the very last exercise, I'm going to stop showing you what to do and just give you an example layout with DRC errors in it and let you find them and fix them yourself. You know all of the commands and methods to solve them. All the problems are ones that I've shown you in the exercises. There really isn't much more I can show you. That's about it for how to find DRC errors, evaluate them, and correct them. So have fun with this last exercise. Your challenge is just to get the DRC errors down to 0, including any antenna checks, and of course without affecting the electrical connectivity of the circuit. Because this isn't a full chip design, you won't be responsible for density checks or generating fill for this one. Good luck.